Hello, my name is Victoria Grimes, and this is my Physics 2 Lab 5. In this lab, we collected observational data of a magnet falling through a conductive tube of aluminum foil. We modeled the tube and magnet's interaction computationally and compared the observed data with computational predictions. The fundamental principles in this lab included the Biot-Savart law that says a moving charge creates a current which creates a magnetic field, so a magnetic field is created by a dipole. Then Faraday's law, which says the magnitude of EMF produced is equal to the closed path integral of the Curl electric field, as well as Newton's second law. Presented here are the results from the experiment. The observed result was 1.29 seconds, while the computational one was 1.031 seconds. The assumptions we made were that the bar magnet represents a magnetic dipole, that air resistance is ignored, and that aluminum foil acts as a non-ferrous conductive tube. Next, we're on to our experimental setup, where the system was the aluminum foil tube and bar magnet, the surroundings was everything else in the environment, and the initial conditions is that the bar magnet is treated as a magnetic dipole a certain distance above the tube. The procedure goes as follows. We assigned a north pole on the bar magnet with the magnetometer app. I used Tesla meter. Then we dropped the magnet down the foil tubing and then recorded the time it took for the magnet to exit, and we repeated this process 5 times. This is the data for the 5 trials, and we found that the average drop time was 1.29 seconds. And furthermore, we have measurements for the geometry of our tubing, where we have tube length, tube width, inner radius, overall radius, the mass of the magnet, and the mu from lab 3. This is the coding for the computational model. In step 1, we just inputted the mass and mu of the magnet, and then in step 2, we created a function to calculate the magnetic field of the bar magnet. This is more coding entailing how to calculate the gravitational force on the magnet and calculating the current in the ring, as well as computing the typical B field at each ring. In this last bit of code here, we were creating a function to calculate the magnetic flux. These were our computational results, and as you can see at the bottom, the time in the tube was 1.031 seconds. On to interpreting the simulation. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise, and how can you know? From above, the red is the counterclockwise, and from below, blue is clockwise. So what happens to the dynamics of the system when you flip the magnet around? The direction of the net magnetic field will be opposite to what was recorded in our experiment. And what does the total time in the tube of your real-world system compare to that of your computational system, and how might the computational system be made more accurate? So our experimental was 1.29 seconds versus our computational, which was 1.031 seconds. And to make this more accurate, we would need more trials. What does the shape of the velocity versus time plot in the previous slide tell you about the forces acting on the bar magnet? So in the beginning, we have a large velocity due to gravitational force, and then in the middle, our F net is 0 as the magnet reaches terminal velocity, and then at the end, the gravitational force takes hold again. Now on to our discussion and conclusion. So, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current would increase so that the magnetic force would increase, therefore the magnet would take longer time to follow through. And what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? The induced current would decrease, so the magnetic force would decrease, so the magnet would take a shorter time to fall through. Thank you for listening.